Hi everyone, welcome back. So, continuing our discussion about finite automata, in this video we'll take a look at a more mathematical definition of automata, and specifically let's just focus on deterministic finite automata for this video. So, let's first draw what an automaton looks like. So, here's my start state, and then this is going to go to, let's say, on 0 it goes to some state, on 1 this goes to another state, and on 0 let's say this one, on 1 let's say this loops, and on 0 it goes to some final state. And similarly I have something for this state as well, so let's just say it loops on 0. So this is basically what my automaton looks like, at least a deterministic automaton. Of course I'll have to have a 0 and 1 transition here as well. So this is my automaton, and let's take a look at how we can describe this mathematically. So the first thing we need is a set of states, which is represented by a q or sometimes a k. We'll just use the q for now, so let's get rid of the k. This is the set of states, so these are my states. Next, I need, from these states I need a start state, so this is my S, which is my start state. And remember that for a deterministic automaton this has to be a single state. The start state has to be only one, and then I can have final states, which can be a set again, because I need not have just one final state, so this is final states. So once again, remember there can only be a single start state, but there can be multiple final states. So this is one element from Q, whereas this F is some subset of Q. So this is what I need to describe an automaton, but this is still not complete. I need to specify what characters can come in my automaton, so that's my alphabet. So this is sigma, my alphabet, and that's almost complete, but we still need just one more thing, which is something that describes where each state goes on some character. So let's say I'm at this state, let's call this q1, this is my q2, this is q3, and this is q4. So what I need now is, where does my machine go, what state does it go to from q1 when it encounters a 0. So we need something for that, and that is called a delta, which is the transition function. So this is called the transition function because that's exactly what it does. It gives you all the transitions between states. So this is my transition function, and all of these together describe a deterministic automaton. So a deterministic automaton can be said to be a 5 tuple, which is composed of the set of states, a start state, a set of final states, the alphabet, and a transition function. So that's our mathematical definition of an automaton. And next what we'll see are some more useful mathematical symbols that are used in automata. But before that, actually let's discuss our transition function a bit more, because we still need to determine its domain, its range. So first off, for a transition function, intuitively what things do you need? You need some state q and you need some alphabet a. So this is what I need, and this is going to give me another state, let's say q prime. So q and q prime are subsets of are elements which belong to q, my set of states, and a is some alphabet. So this is my transition function delta. So its domain is basically just any state Cartesian product with the alphabet. So I take any element from my set of states, I take q1 and then I take a 0. That would be a delta of q1, and 0 would be I think it was q2. We can take a look right here. So Q1 on 0 was going to Q2, as you can see here. So this is my transition function. That's my domain and range for the transition function. So this is basically how my transition function looks. It goes from Q cross sigma to Q again, because Q2 is again some element belonging to Q. So that's my transition function. So let's draw a line here. That ends our discussion about the transition function. And next what we'll talk about is some more mathematical symbols that are useful when dealing with automata. So next what we are going to see is the yields symbol. So it is represented like this, and this symbol stands for, remember this well, this stands for yields in one step. So this one step is very important. So this symbol stands for yields in one step. And what does that mean? It means that, let's say I have some input string, let's call it x, which is, let's say 0010, something like that. Now what I say is I take some state q from my automaton and I take x, and then I say this yields some other state q prime and some other input string x prime. So this, what basically this means is I take, let's say I'm at q1 right now and my input is 0010. So what happens is I don't know what this is now. So what happens is I consume this 0 right here, and I go to my q2 state from the automaton. So I go to q2, and now since I consume this first 0, my input string is now 010. So this yields in one step this thing right here, and then I can say that q2 010 yields in a single step q4. So I have q4 and then a 10 because I consume the first 0 from here, so I consume this one. And that's basically what the yields operator is used for. And very similar to this is another operator, which is just simple yields, or you could say yields in one or more steps. So this is represented with a star. What this means is, let's say I have q1 and I have my previous string, which is 0010. Now what happens here is I can say that this yields, of course this does yield q2 and 010. So 010. This is definitely true because this yields in one step itself, but I can also say that q1 on 0010 yields in one or more steps q4 and just 10. And finally what I can say, going on like this, what I can say is q1 on 0010 does actually yield q4 and epsilon. And now here comes the mathematical definition of whether a DFA accepts a string or not. So what happens is, let's say I have my input x, and this is my input, and I have a start state, let's say q1 or q0, let's call it, not to confuse with our q1 from the automaton that we just drew. So we have q0, which is the start state, and what happens now is we say that if q0 comma the input x can yield in one or more steps the sum q prime comma epsilon, and q prime belongs to f, then accept x, So this is very important. This is how we mathematically define whether a DFA accepts a string or not. So we are saying that if I'm at a start state q0 and I have some input string x, and if that yields in one or more steps q prime, which needs to be a final state, and epsilon, meaning that we have consumed all inputs, all symbols from the string, then we say that we need to accept x. So x is a string that belongs to the language for which we drew the DFA. So that's about the yields operator. Next, what we're going to look at is the last symbol for our for this video. So that symbol is delta cap, which is basically which takes a set, a state, and it takes an input string and it gives you a state again. So it gives you q prime. Now what this delta hat means is just like we had delta, which gives you the next state that it leads to. So what is delta? Delta takes some state and some alphabet. Remember, this needs to be something that belongs to the alphabet. This can't be an entire string. And this gives us some q prime, which is the very next state that the machine is going to go to when it sees that the current state is q and the input symbol is a. That's what delta gives us. Now delta hat here, what it does is it takes some q, which is a state, and then it takes an entire string, and it gives you, after consuming all the symbols from the state, what is q prime that I'm going to end at. So another way to say if a DFA accepts a string is to say whether, so let's say x is my input string. So if delta hat of q0, which is my start state, comma x equals q prime, and q prime belongs to f, then accept x. So that's about the last symbol, delta hat. I hope the difference between delta and delta hat is clear. Remember that a belongs to the alphabet and x could be any string, so it belongs to sigma star. If you remember, sigma star is all strings that are made using the alphabets in sigma. So that's about all the mathematical symbols that are useful when dealing with automata. And in the next video, we'll look at a mathematical definition for non-deterministic automata. So I'll see you there.